Welcome to ECE 4803, Mathematical Foundations of Data Science. Right, so what do we mean by data science? Well, data science is really just all about how can we extract information from data. And when we talk about the mathematical foundations of data science, we're really talking about two main pillars, which are probability and optimization. Probability arises because basically anytime we're dealing with real data that has any kind of uncertainty in it, we need principled ways to model that. Now, optimization, we'll see, kind of comes in a slightly different way. It's really that whenever we have data and we want to extract some kind of information from that data, this often can end up being posed as an optimization problem. We'll be a bit more formal about what that means in just a little bit, but first, let's give a concrete example that also maybe illustrates that data science has been around for maybe longer than you think. A classic result, due to Galileo, is that an object in freefall experiences uniform acceleration in time due to what we now call gravity. Specifically, what uniform acceleration means is that the speed should be linearly proportional to the amount of time that has passed. As a consequence, the distance an object falls should be proportional to the square of the amount of time that has passed. In Galileo's last book, he actually argued that this ought to be the case by appealing to philosophical grounds, so specifically arguing from the philosophy of Aristotle, that this ought to happen. But he went much further than that. So he didn't actually just argue that it ought to be the case. He actually provided an experiment that would show that bodies in nature really do in fact experience this kind of acceleration. And it was a very simple experiment. So what Galileo did was he constructed an inclined ramp with marks indicating points along the path of this ramp. So at a quarter, a half, 2/3, 3/4, and the entire length of the ramp. And then he repeatedly rolled a steel ball down this ramp, measuring how much time it would take for the ball to reach each point. So it turns out you can repeat this experiment even today. So there was a recent modern day reenactment of this exact experiment, and I'm showing you the results. So you see the comparison is the fraction of the ramp that's been traveled versus time squared. And what we find is that there's a very close to a perfect linear set of observations in this data. What Galileo might have done was just to kind of conclude based on visual inspection that clearly this hypothesis has been supported. But note that there isn't a perfect agreement between the data and the linear fit. And you might want to say, well, okay, given this data, how can we actually determine what is really the best fit to this data? And as soon as you introduce this notion of what is the best fit, you immediately come to an optimization problem. In particular, let's look at this problem of fitting a line to a data set. So imagine we have m data points, x1, y1, all the way up to xm, ym. And what we want is to find some f of x that's just a linear function of x, so alpha times x, such that f of xm is approximately equal to ym for all values of m. So the key here is, what do we mean by approximately? Well, one choice, a very popular choice that we'll return to soon, is to simply look at the sum of the squares of the errors. So we're going to look at, say, the average squared error averaging over all m data points. So what we want is to find the best possible line. So we would like to find the choice of alpha that minimizes this squared error. And we can write this as a simple optimization problem that says we'd like to minimize this function given by the average squared error over all possible choices of alpha. This is an example of the kind of optimization problems we'll learn to solve in this class. Now, you might already see how you might go about solving this problem, but it's okay if you don't. We'll return to this in the next lecture. But for now, I just want to emphasize that problems like this arise throughout data science. In fact, much of data science could really be viewed as just an elaboration on this very simple optimization problem we're looking at here. Now, before we really start digging deep into specific optimization problems, I think it's nice to talk a little bit about the history of how we got here, and really, what are the origins of data science. As I was saying earlier, there are really two pillars of data science, probability and optimization, and they have kind of their own somewhat separate early beginnings. And then we'll see kind of where they merge in a very interesting example that we'll talk about next lecture. But first, let's talk about probability. So what are the origins of probability? Well, people have been thinking informally about probability for a long time, but the first scientist who really sat down and gave a very careful accounting of how to think about probabilities in a rigorous way was Girolamo Cardano. Cardano is probably the most interesting scientist and mathematician of the Renaissance that you've never heard of. He was an accomplished physician. He was an inventor. He invented the gimbal and the combination lock. He was a mathematician, so he was the first person to use imaginary numbers, which he found necessary to find the roots of certain cubic polynomials. And most relevant to our story, he had a serious gambling problem. He really did lead a truly crazy life. He was accused of heresy, imprisoned on multiple occasions. He was very superstitious. He was an astrologist, and he actually cast his own horoscope, predicting a death at age 75. But then he lived to be 75. And when he found himself feeling nice and healthy, he actually committed suicide by drinking poison to ensure that his horoscope prediction did in fact come true. Now, for us, what's interesting is that he wrote the first book that kind of rigorously calculated various probabilities involved in certain games of chance, a card game named Primero, and certain games involving dice. This is actually a fascinating book. So I have a copy of it. It contains all kinds of advice related to gambling. So part of this book is all about basically how to calculate probabilities so that you know how to place bets. But maybe more interesting is that it also contains all kinds of other advice that has nothing to do with probability about gambling. There's an extensive section where he just talks about the role of trash talking, and then also includes a lot of really bizarre superstitious advice where he is telling people how to set things up. And part of the advice is like, make sure you have a flat table because people can exploit a slanted table when you're playing a dice game, but also make sure that you're facing your position facing a rapidly rising moon for unexplained reasons. So Cardano, super interesting guy, and really laid the foundation for how people were going to think precisely about probabilities. Now, the next major developments came about 100 years later when Blaise Pascal and Pierre de Fermat in 1654 had an extensive correspondence. This was prompted by a French nobleman who posed a question to Blaise Pascal about how do you divide the winnings in a particular game that's only been partially completed. And this led to a long correspondence that eventually came to the attention of the Dutch scientist Christian Huygens, who learned of this correspondence and in 1657 published the very first book on probabilities. This is a long treatise on problems associated with gambling. Because lots of people were very interested in gambling, probability theory became much more popular, and the subject really rapidly developed throughout the 18th century. And there were a number of contributors during this period, so Jacob Bernoulli, Abraham de Moivre, and someone you might recognize, Pierre-Simon Laplace. And it was really Laplace who took probability and took it beyond the study of concrete games of chance into a really general subject in its own right. So now let's say a little bit about optimization. So optimization has really been around for a long time. We can point to much older examples. Here's a concrete example of what I think might be one of the oldest optimization problems. It's called the isoperimetric problem, and it really just says, among all shapes of a given perimeter, which one encloses the greatest area? So, is it a square? Is it a triangle? Something else? Well, the answer is a circle, and this has been known for a long time. The first proof of this is due to a Greek mathematician, Zenodorus, working in Alexandria in about 200 BC. However, if we're to believe the Roman poet Virgil, this fact had been known for much, much longer. Virgil's Aeneid tells a story of the Tyrian princess Dido, who is supposed to have founded Carthage in about 1000 BC. Dido is supposed to have asked a local Berber king for a plot of land limited to that which could be enclosed in the height of a bull. The king agreed. I mean, how much land could you enclose in the height of a bull? Well, she then proceeded to take the hide of a bull, divide it up into tiny, tiny strips, make a really, really long piece of string, and form a semicircle within which, supposedly, the city of Carthage was later built. So this is an old optimization problem. Did people really know the answer to this 3,000 years ago? It seems possible. So let's flash forward a few millennia to an optimization problem that played a huge role in the formation of not just modern optimization, but in a lot of developments in 17th and 18th century mathematics. So the first problem I want to talk about is called the catenary problem. This is a very simple to pose problem. It is, what is the shape of a curve assumed by a loose string or chain that's been hung freely from two fixed points? So why is this an optimization problem? Well, the assumption is that if we just hang this chain, the shape that it's going to assume will be the shape that minimizes the potential energy of the chain. Now, if this seems like a strange problem to be considering, it actually turns out to have important implications for architects. The reason why is that there's a parallel between the shape of this hanging chain that minimizes potential energy and the shape of an arch that will have the smallest amount of stress. This parallel has been used for centuries by architects when they're thinking about how to construct large buildings. As an example, if you've ever seen the Sagrada Familia in Barcelona, this famously bizarre building, in the basement of this building, you can actually find a model constructed by Gaudi, the architect, more than 100 years ago, that uses this exact principle. So what you see is a bunch of strings with little beanbags hanging on them that form catenaries. And at first this looks very strange. Maybe it makes a little bit more sense if you rotate it around. But this is actually a very important design tool for architects for many, many centuries. And there was this question, what shape would you actually get? Is there a mathematical form for this shape? Galileo conjectured it would be a parabola. We'll see if he's right in a few minutes. Now, the catenary problem is one very important problem. Another, even more interesting one, is the brachistochrone problem. So the problem here is, suppose we have 2 points A and B. A is higher than B. We're going to place a ball at A, and we're going to roll it down a surface to B. What is the shape of ramp that would get this ball from A to B as fast as possible? So what is the sort of curve of quickest descent? Galileo conjectured that this would be a circular arc. So it turns out Galileo is a smart guy, but he was wrong about the answer to both of these problems. However, we should probably be kind of nice on Galileo if we remember that Galileo was working before the creation of calculus. And here we have the person who actually solved these problems, rather generously pointing out that these problems would be really hard to solve without calculus. Calculus plays a very fundamental role in how we think about optimization problems. So this is a quote from Johann Bernoulli, who really laid the mathematical foundation for how we can solve both of these problems and many other similar problems. Before I move on, maybe I should emphasize just how big of a deal this brachistochrone problem was at the time. So this was one of the biggest open problems in mathematics at a time when European mathematics was a rather competitive and fractured environment. So Johann Bernoulli was a prominent Swiss mathematician. He was the younger brother of Jacob Bernoulli. Jacob Bernoulli was basically the PhD student of Leibniz, who you may know as the co-creator of calculus together with Newton. But Leibniz and Newton did not get along. And the Bernoullis were firmly in Leibniz's camp. So they knew about this open problem. What they did was they presented a contest and said, let's see who can actually solve this problem. And they were hoping that they could use this to really demonstrate why Leibniz's calculus was really superior. Something interesting that ended up happening is that Newton found out about it, and the story goes, Newton heard about it while he was at work, walked home, figured out the solution to the problem, and then after he'd solved it, rather than publishing the answer in his own name, wrote a letter to the newspaper posing as a bartender with an amateur interest in mathematics, and then provided his solution. Despite this bit of subterfuge, nobody was fooled. Everyone knew it was Newton. Bernoulli is supposed to have said, "I recognize the lion by his claws." That being said, modern mathematicians find Johann Bernoulli's solution much more satisfying, and it was really Johann Bernoulli who laid the foundation of modern optimization. Perhaps part of the reason why we feel this way was that he had a really good PhD student. Euler was Bernoulli's roommate and later student, and Euler really took up where Bernoulli left off. Euler made huge contributions, but also had a student himself, Joseph Louis Lagrange, who really made huge strides in the late 18th century after Euler. And this really laid the foundation for what was to come next, which is really the fusion of these two threads of probability and optimization, pioneered by Legendre and Gauss in their sort of co-development of least squares, which had huge implications both for optimization and probability. We'll come back to this in the next lecture. But before we do, maybe we should finally say what we really mean when we're talking about optimization problems. So a mathematical optimization problem really consists of three components. The first is some set of decision variables. So say we'll call these x1 up to xn. And these are variables that we have some kind of control over and can set in some way. And we'd like to find the optimal setting of those as measured by some kind of objective function. So I usually use f for this, and this is just some function of those variables that basically tells us how good of a solution we have. So this could represent something that we want to maximize, like goodness of fit or profit or something like that, or some cost that we want to minimize, like error or loss. And then finally, in many problems, we also have a constraint set. So this is some set of restrictions that tell us what kind of values our decision variables are allowed to take. And this might be imposed by physical limitations or budgets on resources or design requirements or any number of possibilities. So given these components, what does an optimization problem look like? Well, it usually just says, let's minimize our objective function over all possible choices of x that live in our constraint set. And this is how we typically write constrained optimization problems. When we talk about this kind of optimization problem, our goal is to find a minimizer, and by that we just mean some x hat that's in our constraint set, such that f of x hat is less than or equal to f of x for all possible x's in our set. And this is what we mean by a minimizer, so this is just something that achieves the smallest possible value of our objective function within this constraint set. And when we find such a minimizer, we call it the solution to our optimization problem. Now, one thing that's worth noting is that saying that x hat maximizes f in x is the same as saying that x hat minimizes minus f in x. And so as a result, we'll generally only consider the minimization problem in this course. Whenever you encounter a maximization problem, you can always turn it into a minimization problem by just putting a negative sign in front of the objective function. So where does this leave us? So in optimization, for our purposes in this class, the big question is, just given an optimization problem, when and how can we efficiently solve an optimization problem? And this is really where we're going to spend most of our time, but it's somewhat putting the cart before the horse, because a second question here that we could ask is, actually, how do we know that a solution even exists? So there are going to be optimization problems that we just can't solve. So if the objective function is unbounded from below, then there is no minimum. It's going to be important to kind of understand, when do we know a solution exists? And kind of a related question is going to be, well, maybe there's a solution, but how do we know whether or not there's many solutions or a unique answer? And what do we do if there's many possible solutions? These are all things that are going to come up in the context of least squares problems, which is what we're going to start talking about next week.